We're dissecting a rampant vulnerability in modern web architecture, cross-site scripting, or XSS. XSS weaponizes the existing trust between a user and a web application. By exploiting a vulnerability in the site's own code, the attacker uses the application as a vehicle to deliver a malicious payload directly into the victim's browser. The exploit relies on a critical failure to validate user inputs. When an application accepts data without encoding it, an attacker can inject unauthorized scripts, typically JavaScript, into content the site generates for other users. To understand the execution of these attacks, we must look at the three distinct vectors. The first is reflected XSS, the second is stored XSS, and finally, DOM-based XSS. We will break down the mechanics of each vector and move into a live environment to demonstrate how these payloads execute and the specific programmatic defenses required to stop them. Neutralizing these threats requires a precise understanding of their execution architecture, allowing us to build a highly functional defense-in-depth strategy. Reflected XSS is the most common and non-persistent variant of the vulnerability. Because the payload is not saved on the target website, the attacker relies on social engineering or phishing to trick a user into clicking a specifically crafted URL. Clicking the link triggers an HTTP GET request. The highlighted malicious string travels from client to server. The server reflects this unvalidated string back in the HTTP response, dropping the malicious code directly into the browser's HTML. Execution occurs the moment the browser parses that response, treating the attacker's script as legitimate code from the trusted website. This delivery method is inherently unstable. Because the server does not store the payload, the attacker must deliver the weaponized link to every target individually. Stored XSS, or persistent XSS, represents a more severe escalation because the payload is saved permanently on the back end. Instead of custom URLs, the attacker targets standard input fields, such as forum posts, blog comments, or profile descriptions. Tracking the payload from a web form, the application writes the raw script directly into the back-end database, making it permanent. When any user navigates to the affected page, the database automatically serves this embedded payload, delivering the malicious script to every visitor. This bypasses the need for victim interaction. Navigation to a trusted page is the only requirement for execution. By poisoning the application's memory, stored XSS converts a legitimate site into a permanent distribution hub for unauthorized code. Server-side sanitization and secure database practices represent only half of the defensive perimeter. A secure backend cannot stop a DOM-based attack, which targets the client-side execution environment directly. In a DOM-based XSS attack, the server is completely blind to the injection because the payload never reaches it. Receiving a clean server response, the browser constructs its local document object model tree. Within this tree, a legitimate client-side script unsafely processes a URL fragment, dynamically writing and injecting the attacker's payload directly into the local structure. Because this happens locally, the malicious script is executed only after the legitimate page has fully loaded and the client-side scripts begin processing data. This shifts the threat model away from the server. Even with a perfectly sanitized database, an application can leak session tokens if its client-side architecture handles dynamic rendering unsafely. Modern browser sandboxing does not fully neutralize unauthorized JavaScript execution. This table shows the capabilities granted by arbitrary script execution. The primary objective is often accessing the document.cookie object to steal session tokens. Stealing a session token allows for complete user impersonation. The attacker can use that token to act on behalf of the victim across the entire platform. Beyond identity theft, attackers deploy keyloggers, manipulate HTML5 APIs for geolocation, or trigger requests to extract data. Unauthorized JavaScript execution grants an attacker full proxy control over the user's interaction with the application, collapsing the security boundary entirely. Because XSS targets unvalidated inputs across the server, the database, and the client browser, a single defensive layer is insufficient. This diagram illustrates the first layer, escaping. Data entering the system is censored by transforming code syntax into encoded HTML entities. This prevents the browser from interpreting user input as executable instructions. The second layer is input validation. This is a whitelist-only approach, where the application defines exactly what data formats are acceptable and rejects anything else. The third layer is sanitization. This involves using specialized libraries to scrub dangerous markup from rich text inputs while preserving safe formatting. These three strategies must work in concert. Relying on only one leaves an entry point for an attacker to manipulate either the backend or the client-side state. We can ground these concepts by examining intentional vulnerable environments like BWAP and WebGoat. In this BWAP mockup, we submit a script payload into a search field. Because the input is not encoded, the server reflects the code back and the browser triggers the pop-up alert shown here. If that same payload is submitted to a comment section, it is stored in the database. It will now execute for every user who views that comment, illustrating the persistent nature of stored XSS. Transitioning to the WebGoat platform, we can demonstrate a DOM-based attack. In this injection, we use an image tag with an onError attribute. It manipulates the local inner HTML directly, causing the script to run entirely on the client side without a server request. Defending against these vulnerabilities requires implementing these layered programmatic defenses at every stage of development.
So, for the demonstration, I'm going to show you the three types of cross-site scripting XSS that we discussed throughout this session. Not only will this be interesting because you'll see how cross-site scripting works on a vulnerable web application, but it will also help you better understand the concept itself. Now, performing cross-site scripting on random websites or applications is illegal, so we cannot target any real application. Keeping that in mind, I have chosen the Broken Web Applications project. This project is brought to us by OWASP, which stands for Open Web Application Security Project. The Broken Web Applications project, also known as BWAP, is an intentionally vulnerable web application. It contains many commonly known security vulnerabilities and is widely used by security enthusiasts, students, and ethical hackers to practice and improve their skills in a safe environment. To get started, we first need to download a few files and prepare the setup. First, we need to download the Broken Web Applications project. I'll leave the download link in the description in case you want to practice on your own. Secondly, we need to install VirtualBox. Once both files are downloaded and installed, and the Broken Web application is set up inside the virtual machine, we are ready to go. I've already completed all the setup steps. As you can see, the Broken Web application is already running on my virtual machine. This is the OWASP virtual machine, and it's based on Linux. If we run the ifconfig command, we can see the IP address it is running on. As you can see, it's running on 192.168.146.4. If we open that IP address in the browser, we get the portal page. For this demonstration, I'll be using both the Broken Web Applications project and WebGoat. First, let's head over to BWAP. We are greeted with a login page. The credentials are bug. After entering the credentials, click on Login. Once logged in, you'll see a panel where you can choose different vulnerabilities and security levels. Since this is a simple demonstration, I'm setting the security level to low. The first thing we'll test is reflected cross-site scripting. Reflected XSS is mostly related to GET requests when coding on the back end. So first, let's choose reflected XSS using the GET method and click on Hack. We are presented with a form. Forms are a great way to demonstrate reflected XSS because attackers often try to trick users into filling out malicious forms or entering data into manipulated input fields. If we leave these fields blank and click Go, you'll notice the URL changes. You can clearly see the input fields reflected directly in the URL. This means the application is accepting unencoded input, making it a good environment for practicing web vulnerability testing. If I were an attacker, I would try injecting a script here. For example, script alert. This is an example of reflected XSS. Script. When this script is executed, the web application renders the JavaScript as part of the page, and we receive an alert pop-up. This demonstrates how reflected cross-site scripting works. As you can see, the application executed our JavaScript successfully. In a real-world attack, this malicious URL or form would usually be sent to the victim, and the victim would have to interact with it for the attack to succeed. Modern applications often apply filters and input validation to prevent users from injecting raw JavaScript or unencoded input into forms. So that was reflected cross-site scripting. Now let's move on to stored cross-site scripting, which is considered one of the most dangerous forms of XSS. As discussed earlier, comment sections are one of the most common places where stored XSS vulnerabilities occur. Hey, we already have some comments added for testing purposes. In stored XSS, the attacker injects malicious code into data that gets stored in the database. Whenever someone loads that page, the script automatically executes. Let's first add a normal comment. For example, "Hey man, nice work." If we click submit, you'll notice that another script already stored in the database gets executed. That demonstrates how persistent XSS works. Now, for demonstration purposes, let's inject another script ourselves. Script alert, hello world. Script. When we submit it, the script executes immediately. Now we actually have two malicious scripts running on the page one after another. This means that if anyone visits this page later, those scripts will automatically execute because they are permanently stored in the database. Now it's time for DOM-based cross-site scripting. When I first used this application, I realized there wasn't a proper section for testing DOM-based XSS, so we'll use another application called WebGoat. The login credentials for WebGoat are username, guest, password, guest. I've already logged in. If we navigate to the cross-site scripting section, you'll notice there isn't a direct DOM-based XSS option. That's because it is included under Azure Security. DOM-based XSS is a client-side vulnerability. Unlike reflected or stored XSS, which are generally processed on the server side, DOM-based XSS happens directly in the browser through client-side technologies like JavaScript and HTML. Suppose we try injecting a normal script. Script alert, hello world. Script. Nothing happens because the input is being encoded properly. However, if we inject something that manipulates the browser's HTML rendering directly, we can trigger the vulnerability. For example, img src equals x1er equals alert. This is an example of DOM-based XSS. As soon as the browser processes this HTML, the JavaScript gets executed automatically. Notice that we didn't even press submit. The payload was triggered immediately after the browser completed rendering the HTML element. This happens because the client-side code is directly manipulating the DOM without proper sanitization. So guys, that was the demo for today. If you have any questions, feel free to leave them in the comment section below. And if you enjoyed today's session, don't forget to like the video and share it with your fellow security enthusiasts.